In this video, we're going to continue our work with probability and look at the OR rule for mutually exclusive events. To begin with, we're going to look at some of the basics. We'll then go on to answer some questions, and then finally we'll look at some theory behind mutually exclusive events and the OR rule. So let's start with mutually exclusive events. Two events are said to be mutually exclusive if they can't happen at the same time. Let's take a fair six-sided dice. So we have an equally likely chance of getting any of the numbers from 1 to 6. So let's list out the possible outcomes. So 1, 2, 3, 4, 5 and 6. What I'm going to do is define some events. So we'll put some events here and we'll say now the events we will have the following. So event A is now rolling a number 2. So rolling a 2, so let's just put this here, roll a 2. Event B, a different event, we're going to have now roll an odd, so roll an odd number. And then finally we'll have C, so event C, and we'll have roll, we'll go for roll a square number. So roll a square number. So if we look at these, rolling a 2, well there's 1 2 out of 6. B, rolling an odd, 1, 3 and 5. C, rolling a square, we've got 1 and 4. 1 and 4 are the square numbers. So which of these are mutually exclusive events? Which can't happen at the same time? Can A and B happen at the same time? Can we roll a number 2 and an odd number? The answer is no, as 2 is even. So A and B are said to be mutually exclusive. What about A and C? Can we roll a number 2 and a square number? The answer is no. 2 is not a square number, so A and C are mutually exclusive. What about B and C? Can we roll an odd number and a square number? The answer is yes, because we've got the number 1. So B and C are not mutually exclusive. They can happen at the same time. Let's look at our deck of cards. So with the deck of cards now, we've got aces, clubs, hearts and spades. We've got red cards and we've got black cards. So let's go ahead and look at some possible events and see which would be mutually exclusive. So let's go for event A, and this is going to be now picking an ace. Event B, we're going to have now a red, so let's have a red card. And event C is now picking a spade. Remember, a spade is a black card. So can we have A and B happen at the same time? The answer is yes, as we can have a red ace. We could have the ace of hearts or the ace of diamonds. So A and B are not mutually exclusive. They can happen at the same time. What about A and C? An ace and a spade? The answer is yes, as there is an ace of spades. So A and C can happen at the same time, so they are not mutually exclusive. What about B and C? Can we have a red card that's a spade? The answer is no, they cannot happen at the same time, as spades are black cards, so B and C are said to be mutually exclusive. Let's move on and look at the OR rule. I'm going to write this out formally, then explain exactly what it means. If we have mutually exclusive, or I should say, well, in general, if we have mutually exclusive events, we can say now the probability of A or B is simply now given as the probability of A plus the probability of B. So if we have mutually exclusive events, we can use the OR rule. This looks quite overwhelming. It's really quite straightforward. So let's now find the probability on our fair six-sided dice, the probability of obtaining with one roll a number 3 or a number 5. This is simply given as the probability of a number 3, add to it now the probability of the number 5. So if we go back to the last video, the probability of something happening is the number of favourable outcomes divided by the total number of outcomes. So if we look now, the probability of a 3 or a 5, or the probability of a 3, there's 1 3 out of 6 sides. And if we look at the probability of a 5, there's 1 of those out of 6. 1 over 6 plus 1 over 6 will give us 2 over 6. And if we wanted to simplify our answer, we could write it as 1/3. So for probability of A or B, we're just adding them together if they're mutually exclusive. We can see that's the case here. So if I wanted to find out the probability of, let's say, a 4 or a 5 or a 6, these are mutually exclusive events. We'd have the probability of a 4 plus the probability of a 5 plus the probability of a 6. We're just adding them together. So we'd have 1/6 plus 1/6 plus 1/6, and that would give us 3/6. We could say 3/6 or 1/2. And you can just count up. You can see how straightforward it is. We've got now the choice of a 4, a 5 or 6. Well, that's half of them. So this is the formal approach. All we're saying, if we have mutually exclusive events, we simply add the probabilities if we're using the OR rule. Let's also look at a different way that we could have done it. Let's have a look at another example. Let's say the probability now of not getting a 5. The probability of not getting a 5 could be written as the probability of a 1 or a 2 or a 3 or a 4 or a 6. Alternatively, as we saw in the last video, the probability of something not happening is 1 minus the probability of it happening. So we could say it's 1 minus the probability of a 5. If we went for this particular approach, it would be 1 minus 1/6, which would give us now 5/6. Of course, if you've gone that way, you've got this one plus this one plus this one plus this one plus this one. You've got 5 lots now of 1/6s. So you can see exactly the same approach. If these are mutually exclusive events and we want to find the probability of something happening or something else happening, A and B, we just add them together. So let's go ahead and answer some questions. We're asked to decide if each pair of events, A and B, given below, are mutually exclusive. So if they're mutually exclusive, they can't happen at the same time. Can these happen at the same time? Winning a football match and losing a football match. They can't happen at the same time, so these are said to be mutually exclusive. Those two things can't occur at the same time. Selecting a diamond from a pack of playing cards and selecting a king from a pack of playing cards. Well, we can have the king of diamonds, so these are not mutually exclusive. They can both happen at the same time, as we can have the king of diamonds. Selecting an ace from a pack of cards and selecting a queen. Well, we can't have an ace that's a queen. They both can't happen at the same time, so they are said to be mutually exclusive. Okay, let's be careful with this one. It rains tomorrow, it is sunny tomorrow. Both of those things could happen. If they said it rains tomorrow and it doesn't rain tomorrow, then we're looking at a different scenario. So it rains tomorrow and it's sunny tomorrow. These are not mutually exclusive. They can both happen. So you can have the morning of rain and the afternoon of sun. Or it could be rainy and sunny, as it is in some tropical places. So are they mutually exclusive? Can they happen at the same time? These can't happen at the same time. These can happen at the same time. These can't, but these can. Okay, we're now told a bag contains 6 red counters, 5 blue counters and 4 pink counters. A counter is selected from the bag at random. We're asked to find the probability that the counter is A, either red or pink, B, not pink, C, not red, D, blue or pink. So all we're doing is working these out. These are mutually exclusive. So let's look at the probabilities. We got 6 red, 5 blue, and we got 4 pink. That's 15 in total. So we can say that the probability, and I'm going to write it as the probability of red, would be 6 out of the 15, which of course if we wanted, we could simplify. We could say now the probability of a blue, well there are going to be 5 out of 15. And now the probability of a pink, so probability of a pink, is going to be 4 out of 15. Remember, all of these probabilities have to add up to 1. These are all of the possible outcomes that we've had. So we can have a red, we can have a blue, or we can have a pink. We're told that there's no other colours in there. So all of these have to equal up to 1. So let's do part A. we can say either red or pink. So what we're going to have then is the probability of red or pink. All I need to do is add them together. So I'm going to have 6 over 15 plus 4 over 15, which is going to give me 10 over 15, which if we wanted, we could simplify now to 2 over 3, dividing the numerator and the denominator by 5. So just dividing the top and bottom of the fraction by 5. I could have simplified all of these, but if we're adding them, it's often easier to leave them with this common denominator and then simplify it later. So not pink. So what we could do is add all of the others, or we could say now the probability of not a pink will be 1 minus the probability of a pink, which is going to give us 1 minus 4/15. If we think there are 15 fifteenths in a whole, so this is going to give us 15 minus 4, which is 11 fifteenths. Alternatively, I could have just said that this was equal to the probability of a red or a blue. I think it's a lot easier to do 1 minus the answer. So if we look at the next one, the probability, so that's B, so let's put B here, the probability in C of now not a red. So the probability, let's just put that there, probability now of not being a red will be 1 minus the probability of it being red. So that's going to give us now 1 minus 6/15. 15 minus 6 is 9. 9/15, which if we wanted, we could simplify and we could divide the numerator and the denominator by 3 to give 3/5. If we look at D, a blue or a pink, and we'll do it just here. So the probability of a blue or a pink, so blue or pink, well, the probability of a blue is going to be 5. So let's write this down, 5 over 15. And the probability of a pink is 4 over 15, which gives me 9 over 15. If I wanted to simplify, I could write this now as 3/5, dividing the numerator and the denominator by 3. So that's what we would have. Now if we look at this, a blue or a pink and not a red, well, if it's not a red, it's a blue or a pink. So we can see from this is exactly the same. So not red must be blue or pink. So we could have linked those two together. Essentially, this is asking us the same question. So do check those two things link together. Okay, so that now is looking at using the basic rule. You're not expected to use all of this heavy notation, such as the one that we were looking at to begin with, this right here. You're just simply adding them together if they're mutually exclusive. Okay, as part of a project, a group of students classify each day as dry, damp, wet, or very wet. The probability that a day will be dry or damp is 0.6. The probability that a day is wet is 0.3. In part A, it says, what is the probability that a day is very wet? Remember, these have now 4 possible outcomes. All of the outcomes must sum the probabilities to give 1. So if we look now, we've got dry and damp, which is 0.6, plus 0.3, which is for wet, plus now very wet, so I'll leave that as V, must be equal to 1. So 0.9, we can see very wet must be equal to 0.1. All we're doing is finding now what sums to give 1. These are the only possible outcomes. So if we were listing the outcomes, it would be dry, it would be damp, wet, and then very wet. Okay, no other possibilities from there. So let's go ahead now and work on the questions. It says, we're asked now, it says the probability that a day is damp is twice the probability that it is dry. We're asked in part B, what's the probability that it is damp or wet? So what we're looking for is the probability of now, and I'll say that this is DA, damp, or W, which is going to be wet. If we look here, we've got now dry or damp is 0.6. We're told here the probability that the day is damp is twice the probability that it's dry. So if we look at this now, what we're going to have is damp would be 0.4 and dry is 0.2. These equal up to 0.6, and being damp is twice the probability that it's dry. So what we've got now is the following. This is going to give me from here, damp is going to be 0.4, and then we're going to add to that now the probability of it being wet, which is 0.3, and we can say that that is going to be 0.7. So that gives us our final answer. And if you think about that, very wet is going to be 0.1, and then we can say that dry is going to be equal to 0.2, and all of these will always add up to 1. So a bit more working on here, but we should know that all probabilities sum to give 1, and we can simply work this out using the OR rule by adding together. Okay, let's look at another question. In a class of 25 students, there are 8 students with size 6 feet, 4 students with size 7 feet, and 3 students that are left-handed. In part A, we're asked to find the probability that a student in the class has size 6 or 7 feet. So let's just write this out. So what we can say then is the probability of size 6, so size 6, will be equal to, we've got 8 of them. There are 8 students of 25. So 8 out of 25. We can say the probability now of size 7, let's write this down, and how many have we got? We've got 4 out of 25. If we now look at the left-handers, so left-handed, probability now of left-handed, we're going to have a total here of 3. What I can do at this stage is write some more information. So if we wanted, we could from this, and I think we'll answer the question first. Let's just answer the question. So let's do part A. Probability of 6 or 7 is simply now the probability of 6 added to it the probability of 7. So that's going to be 8 over 25 plus 4 over 25, which is going to give us a total of 12 over 25. So what that tells us then quite clearly is that 13 of the 25 either have size 5 or less, or 8 or more, or if you like, aren't size 6 and 7. So the probability that a student is right-handed, well, what we're going to do is now 1, so I can say the probability of right-handed is going to be equal to 1 minus the probability of left-handed. Again, you can just think, well, you're either right-handed or left-handed, so we've got to make that up, and we know it's going to be 22, or we could do 1 minus that. So we could say that this is simply going to be now 22 out of 25. All I've done is simply said to myself now, the probability of being right-handed must be 1 minus the probability of left-handed, or you can say how many pupils make up the 25. Okay, so what we've got here is the following. It says now, is it possible to find the probability that C, a student has size 6 feet and is left-handed? The answer is no, as they're not mutually exclusive. D has feet that are bigger than size 7. The answer is no. We can work out, and I think this is going to be the next question, has feet that are not size or 6 or 7. Yes, we could work this out, as we got 6 or 7 to be 12/25. So the probability now of not, so let's write this in, not 6 or 7, let's write that there. We could say that this is going to be 1 minus 12 over 25, which gives us 13 over 25. But we don't know if all of those are 8 or more, or they're 5 or less. So on the first two, we can't work it out. On the third one, we could find it out. So do look at the wording and work from there. So nice questions and typical of what we might get. Okay, let's move this on a little. Let's now look at the idea of mutually exclusive events. So at this stage, if you've done enough and that's as much as you wanted to do, that's perfectly fine. I'm now going to go into it and look at it slightly deeper and start using some Venn diagrams. What I'm going to have now are two Venn diagrams. The first one on the left is an example of where we might have mutually exclusive events. So these can't happen at the same time. They have no intersection. So let's look at an example now of the following. Let's take event A, and we'll have event A. So event A is going to be, and we'll have, let's go for a prime number. So event A is a prime number, and event B is going to be we'll go for a square number, and we'll take our fair six-sided dice. So we've got 1, 2, 3, 4, 5, and 6. So let's put these in these circles. So, or if you like, ellipses. So the prime numbers. Well, this is a prime number, this is a prime number, and this is a prime number. So what we can do is put these in. The prime numbers are going to be 2, 3, and 5. If we look at the square numbers, we've got 1 and we've got 4. So 1 and 4 are going to go in this one. And then finally on the outside, which we call the universal space, is 6. 6 is neither a prime number or a square number. We can see that we've got no points of intersection. These are mutually exclusive events, and we can say in this case the probability of A or B is simply going to be equal to the probability of A plus the probability of B. They are mutually exclusive events. They can't happen at the same time. Let's now look at C and D. If you want, you can use A and B again. I'm just going to use C and D, and we will look at the following. So this one we're going to have C, and this one we're going to have D. So sticking with our fair six-sided dice, what we're going to have are even numbers and square numbers. So we'll have even, so let's look at even, and we will have square numbers. So if we think about this now, we'll start with the square numbers. The square numbers are 1 and 4. The even numbers are 2, 4, and 6. So if I just write this out, the even ones are going to be 2, 4, and 6. The square ones are 1 and 4. We can see now that 4 is common to both. So that would go in the middle. That leaves me 2 and 6 here, and it leaves me 1 here. That must mean on the outside, those numbers that are neither even nor square are 3 and 5. If we look at this, we have an example that these are not mutually exclusive events. So if I roll that dice once, I could get an even and a square number. If we want to think about this now, let's write this out. If I wrote now the probability of an even, so let's write this out, even or square, if we use the rule that we were using, we would simply add these up. Now that's going to give me here 1, 2, 3, 4, 5. So we would say that this is 5 out of 6 if we went ahead and used this particular rule. And that's why it doesn't work when we have these particular events here. So that the mutually exclusive one works, but if they're not mutually exclusive, we don't do it. And this is where it goes on to something slightly more interesting. Later on in your studies, you will see that the probability of A union B, and I'm going to write it like so, will be equal to the probability of A plus the probability of B minus the probability of A, and then we have intersection B. As stated, this is certainly beyond the scope of this video, but it's interesting nonetheless. So all we do is add them all up and then subtract away the one that we've counted twice. And we can see what that's going to do. So if we add all of these up, we're going to have now the probability in this particular case of C and D. We're going to have now 3 over 6 plus 2 over 6. And then we're going to subtract away the one in the middle, which is both of them, and that's going to be 1 out of 6, and we can see that this is going to give us 4 out of 6, or we could break this down to say 2/3. So we can see exactly why now the probability of A and or B, and this is what we call the union, and later on you will look at this, A and or B is the probability of A plus the probability of B minus the probability that it is both A and B, or in this case, both C and D. So do you need to know that? I think certainly if you're taking your work forward when we have events that are not mutually exclusive, it's interesting to look at these on Venn diagrams and work them from there. So that last bit's sort of to increase the understanding a little, but certainly at the lower end of the course, you will simply need to be able to work out adding these probabilities.